Well, good morning there, physics students. Hey, it's Wednesday, May 6th, 2020. We're going to go through a little bit of physics. So today, goals, I can explain the concept of conservation of momentum, and I can perform calculations related to conservation of momentum. Now, actually, before I get into the conservation of momentum, I want to look at one of the problems that you were assigned on Monday, and this is problem number 3 from page 193 in your textbook. And what I've seen in the past is a lot of students make a mistake on this one, so I want to talk you through it, see if you made the same mistake. If you did, now you can learn from that mistake. If not, you can pat yourself on the back. Okay? So we have in problem number 3, a soccer ball is going north at 18 meters per second. It's a 0.40 kilogram ball. And a player kicks the ball, and now the ball is going south at 22 meters per second. Still the same ball, so still 0.40. And so we're looking for what is the impulse. Okay? The question says, what is the impulse? And so we know that impulse is the change in momentum. In other words, it's the mass times the change in velocity. Now, it would also equal force times change in time. But you know what? We weren't given any information on force or time, so if I don't have to get into that, I don't want to. Okay? I can look at what is the change in momentum. It's the same ball, so the mass didn't change, but the velocity changed. Okay? So, all right, my impulse is my mass times the change in velocity. Well, how do we find the change in velocity? We have a final velocity minus an initial velocity. Okay? Now, what's going to be really important is for you to recognize that these two have direction. All right, and so the typical standard that we give is that north is going to be in the positive direction and south is going to be in the negative direction. So when we look at these numbers, this is a positive 18 meters per second, but this is actually a negative 22 meters per second when we do our math because it's in the opposite direction. And that was the final velocity, right? The final velocity. This is after the kick. I'm going to plug in my numbers here. My mass was 0.40 kilograms. My final velocity is a negative 22 meters per second. And now I'm subtracting my initial velocity, which was a positive 18 meters per second. So this is where the students make mistakes, by not putting that negative on there. The difference in velocity here, the change in velocity, is actually going to be a 40 meter per second change. It was going 18 meters per second this way, and think about, you have to take away all that 18 plus add another 22 more in the other direction. That's a 40 meter per second change. So to finish this problem off, we've got 0.40 kilograms times negative 40 meters per second. Grab a calculator. I should be able to do that in my head, shouldn't I? 4 times 4 is 16. Negative 6. I think this is just negative 16. I'm going to use my calculator because maybe my mental math is off. 0.4. Yeah, I can move the decimal point one place that way and move it one place that way, and I got 4 times 4. Negative 16 kilograms times meters per second. None of those labels cross off. All right. My impulse is negative 16 kilograms times meters per second. It's my change in my momentum. My momentum changed. This basically means it's in the other direction by that much kilogram meters per second. Okay? So take a look at your problem number 3 on page 193. See how you came out. If it doesn't make sense, watch it again. If you're still stuck, give me a call. So let's talk about conservation of momentum. There's lots of situations in the world where things run into each other. We have collisions. And if during the collision there's no outside input of force, then the momentum is conserved. Okay? If you've ever played pool, you have you strike the cue ball, you impart an outside force to the cue ball to make it move. Now the cue ball is rolling across the table and strikes another ball. The total momentum, if you could just draw a box around all the balls on the table, the total momentum as they hit each other stays the same. Now the momentum might change. The cue ball might lose some of its momentum and the other ball gains momentum, but the total stays the same. That's what conservation means in science. Stays the same. So we're going to think about our system. Just imagine we're going to draw a box around everything. And the way I analyze problems, and it's a little bit different I think than your book describes, but the way I analyze a conservation of momentum problem is I just think about what do we have before the collision. I look at what is the total momentum before the collision, and what's the total momentum after the collision, and it has to be equal if momentum is conserved. Now when I do this math, I have to consider all the objects. So if there's multiple objects, I have to consider the mass and velocity of each object before the collision and after the collision. Let's take a look at a couple of samples to see how that works. Okay, so here we got a guy sitting in a rolly chair, and our guy weighs 185 pounds. He's not moving, 0 meters per second. And here comes a medicine ball. So somebody does a 2-hand chest pass, boom! And the chest pass is coming in. This is a 5 kilogram medicine ball, and medicine ball is coming in at 9.35 meters per second. And the guy catches the ball. Now you can think, the ball is going to slow down when he catches it. But if he's in a good rolly chair, he should take off going backwards. So right now we're going to ignore friction between the chair and the floor, and we're going to ignore friction in the wheels. We're going to say, if this were a frictionless situation, how fast is this guy with the ball going to be moving? And the way I look at it is the momentum before has to equal the momentum after. Momentum before equals momentum after. Okay, momentum before. Well, what's moving? First of all, this guy isn't moving. So mass times velocity, if the velocity is 0, then the momentum is 0. So this guy starts out with 0 momentum, but the ball is moving. So I'm going to have the mass of the ball times the velocity of the ball. Because that's the only thing that's moving. The guy's not moving. This expression describes my momentum before the collision. Now after the collision, you can kind of think in this case that the guy caught the ball, and so we could use the mass of the ball and the guy together, or we could still treat them as 2 different objects. I'm not sure what your preference would be on this. For this one, I'm going to imagine that they turn into one object. So for the mass, I would have the ball plus the guy, because that's the mass of what's moving now. And then there's just going to be one velocity, because they're moving at the same velocity now. Okay? So to do my math, I'm looking for this velocity. Okay, I just call it V prime to say that that's our new velocity. So V prime is going to be the mass of the ball times the velocity of the ball divided by the mass of the ball plus the guy. Okay. All right, mass of the ball is 5.00 kilograms. The velocity of the ball, 9.35 meters per second. And I got to divide by the mass of the ball plus guy. And here is where I get just a little bit of problem. This was in kilograms, this was in pounds. So I just want to go somewhere off on the side and do a little conversion factor. There's 2.2046 pounds in 1 kilogram. So what's the mass of our guy? 185 divided by 2.2046 equals 83.9 kilograms. So the mass of the guy plus the ball is going to be 88.9. So 83 plus 5 is 88.9. 88.9 kilograms. Looking at labels, kilograms are going to cross off. And altogether, I got 5 times 9.35 divided by 88.9. And I come up with a new velocity of 0. Looks like I get 3 sig figs.
This is Lisa Nowak, Retail Extension
5,
8, Mrs. Nowak,
2,
Retail Extension 168.
6 meters per second. Right, does that make sense? So the ball's coming in at almost 10 meters per second, 9.35 meters per second. But now I catch it. I got a lot more mass than, well, now I got a lot more mass than this guy too. But okay, the guy catches it. Now the ball slows down, so the ball loses some momentum, but that momentum transfers to the guy. The total momentum of the system stays the same. So now we have 88.9 kilograms moving at this velocity. That is the same momentum as 5 kilograms moving at that velocity. Okay? Let's look at another one. So, here I have a rifle with a bullet in it. Okay? And right now, it's stationary. The rifle has a mass of 3.80 kilograms. The bullet has a mass of 10.7 grams. When the bullet is fired, the bullet comes out of the muzzle at 914 meters per second that way. So let's think this through. If we look at conservation of momentum, we say that the momentum before has to equal the momentum after. Well, the momentum before, the gun wasn't moving, or, the rifle wasn't moving, and the bullet wasn't moving. The momentum before is 0. How's that going to equal the momentum after? Well, see, the bullet's coming out flying this way. And that's going to be a small mass going at a high velocity. Mass times velocity gives us momentum. But the gun, which has a quite a bit larger mass, the gun's going to be going back this way. It's going to have a kickback. Let's calculate the kickback velocity of this gun. So how do I write this expression? After, the bullet's going to be moving and the gun's going to be moving. So I'm going to have the bullet is going to have the mass of the bullet times the velocity of the bullet. And the gun is moving, so I'm going to have the mass of the gun times the velocity of the gun. And that all has to equal 0 because before the shot was fired, the gun wasn't moving. Okay. So I can plug in some numbers. 0 equals, well, maybe I don't want to plug in numbers right away. Maybe I want to do some algebra. I'm looking for the velocity of my gun right here. So algebraically, I got to work from the outside in. I'm going to subtract minus mass of bullet, velocity of bullet is going to equal mass of the gun, velocity of the gun. And then I'm going to divide by the mass of the gun. So I can cross that off. And I know that the velocity of my gun is going to be negative the mass of the bullet times the velocity of the bullet divided by the mass of the gun. Okay, the mass of the bullet. Do you think it would be a good idea to put the masses in with different labels? I hope you don't think that's a good idea. 10.7 grams. 10.7, I got to move my decimal point 3 places. That'd be 0.0107 kilograms. And the velocity of the bullet, 914 meters per second. And the mass of the rifle was 3.80 kilograms. And we can see that kilograms cross off. It's going to leave us with meters per second. So the velocity of the gun is going to be, let's see. Oh, I forgot my negative in here. So make sure we get that. And I just know my answer is going to be negative in the end. So I don't type that negative into my calculator. I just put it on my answer. Got 0.0107 times 914 divided by 3.8 equals negative 2.57 meters per second. Okay. Now I know that there's at least a few of you in class who are hunters. And I didn't grow up in a hunting family, but you know, my dad gave me a couple of lessons. And so I remember first time shooting shotgun, and you know, Dad was very, very adamant about make sure that you pull that stock back against your shoulder. And there's perfectly good physics reason for that. Okay, if I don't have that against my shoulder, when you pull that trigger, that gun is now going to kick back at about 2.57 meters per second. Actually, that shotgun probably might have more kick than that. That's not the problem I did. This was based on a .308 caliber with a 165 grain bullet. I actually looked up numbers to fit this problem. So that's going to kick back and it's going to hit me, and that could hurt. Okay. Now, what's the difference if you have it against your shoulder? Well, now you become kind of attached as part of the mass of that gun. So now the kickback isn't just affecting the gun, it's affecting all of your mass too. And the bigger you make your mass, the smaller this kickback velocity effectively is going to be. Okay? Maybe you know people. I know someone who's a very experienced hunter who still sometimes makes mistakes. He was out looking, looking at a deer through the scope, didn't have it anchored quite as tight as he can be, and when he pulled the trigger, the gun kicks back, the scope hit him above the eye, cut his eye open, and knocked him out. Actually blacked out for a bit. Wakes up, touches his forehead, blood all over the place. Dangerous stuff. Okay? Got to be aware. It's conservation of momentum. So, there's a couple of sample problems. Time for you to start. You got to practice. You got to see where you're getting stuck. You got to let me know what I can help you with. Take care. Hope to see you soon. Bye-bye.